Okay, so this video we're going to be talking about colligative properties and pretty much reviewing what I'll be asking you on your test, more or less. So, with your colligative properties, the two that I'm focusing on are Raoult's Law and Osmotic Pressure. So the first one we're going to go over is Raoult's Law. Or I don't know why my pen decided to stop working. Great. There we go. Anyways, so first things first, Raoult's Law. So the overall idea of this is you have the pressure of a solvent is equal to the mole fraction of the solution times the vapor pressure. So the vapor pressure of the pure solvent. So what that means is, say you had, I'm going to use water because it's easy, as there's a lot of tables on this and I don't have to look anything up because I have it right in front of me. So say we have some water and the temperature of said water is, we'll do 20.5. So it's 20.5 degrees Celsius. So at this pressure, the vapor pressure it's very low, but it's 18.1 millimeters of mercury. So that's the amount of solvent that's turning into a gaseous form. It's, going from liquid to gas. And it's equalizing with the air pressure. So essentially what's happening is we have a very small amount of pressure from the water that is turning to vapor. So if you remember, 18.1 times times 1 atmosphere divided by 760 millimeters of mercury, and you would cancel that. That's going to be a pretty small number. It's going to be less than 0.1. So that shows you that it's not a lot of pressure at this temperature. Now, say I had the same beaker, same water, same everything, and I add some heat to it. Say it's 100 degrees Celsius, which is, as you know, the boiling point of water. So let's do 100 degrees Celsius. I don't know what happened there. Your vapor pressure, and that's when you start seeing the bubbles. Your vapor pressure is going to be 760 millimeters of mercury because it's turning to gas. So, anyways, something interesting that was discovered a while ago is if we add in another something to mix into the solvent, it's going to adjust the boiling point to, it's going to adjust the vapor pressure, not the boiling point. It will adjust the boiling point too, but that's not what I'm explaining right now. So we're going to go over some problems as to how this works and how you can solve it. They're super simple. And if you have any questions, make sure you go to office hours and ask me. So let's do a simple one. So at a temperature of, let me get my table so I have the starting solvent. So at a temperature of 16.5 degrees Celsius, the vapor pressure, so that is represented as this, of water is, I said 16.5 14.1 millimeters of mercury. Let me see how I wrote this. So let's say we had 37 grams of lithium chloride are added to, 4.23 liters of water. What is the new vapor pressure of water? So what's the new? So there's a few things you have to do here. One, we already know that this is this. That's not changing because we're at this temperature. It's not saying that it's changing. Now, you've been given a liter amount of water, and you're thinking, well, I can't change that to moles. Yes, you can. So if you have 4.23 liters, that means that you have 4,230 milliliters, which, if you remember, the density of water is 1 gram over 1 milliliter. So right there, you've changed all of this to grams. So that means you have 4,230 grams of H2O. Now, we're not done with H2O because we still have to multiply it by its molar mass, or divide it by its molar mass to get the moles. So we take 4,230 grams of H2O times 1 mole divided by 18 grams of H2O, and then that will give you your moles. So we have 235 moles of water. All right. So this is important. Wow, did I run out of room already? Oh. Okay, so now, lithium chloride. I'm going to just look this up on my phone. So lithium chloride is 42.300. We'll just put 42.39 grams a mole. So we have 37 grams. So you have 37 times 1 mole divided by 42.39, and that's going to give you the moles of that. So you have 37 So we have approximately 0.87. So both of these are important. So I'm going to copy all of this and take it to the next page. If you need to copy it, just pause the video. Okay. So the mole fraction is just telling you how many moles of solvent you have compared to solute. So the way you calculate this is moles of solvent divided by mole solvent plus mole solute. So this would be 235 moles. I mean, you don't even have to write the moles. You know what they are. So you have 235 divided by 235 plus 0.87. All right, so your mole fraction is 0.996. Okay, so we have to figure out what the new vapor pressure is. So we need this, and we have the original vapor pressure. So now all you do is just plug everything in. 14.1 millimeters of mercury times 0.996. And technically I wrote this in backwards, so let me rewrite this. 0.996 times 14.1 millimeters of mercury. And then we'll plug this in the calculator. So our new pressure is 14.04. And while it didn't change a lot, the presence of that small amount of lithium chloride changed the amount of pressure from the water vapor. And that's essentially what Raoult's Law is explaining. Pretty much like that's all I'm going to be asking you about Raoult's Law in terms of tests is calculating what the vapor pressure is. But with osmotic pressure, there's a few different things I could ask you to solve for. So we're going to go over some quick stuff because I've already gone over osmotic pressure quite a few times. So let's see. Anyways. Alright, so with osmotic pressure, usually you're going to have like some sort of tube array or something like that. In your body, it's just the cell barriers or the membrane of the cells. So over here, you're going to have your solute or your solution. And over here, you're just going to have your pure solvent or water or whatever. And this is your membrane. And again, flows this way. But you're going to have some sort of pressure from the outside pushing down on that. And if it's enough that can push all of the solvent back in across the semi-permeable layer, it's going to prevent osmosis from happening. So I'm going to do just one problem super quick, and that's it. So remember, pi equals mRT. It's the same thing almost as the ideal gas law. It just, I is a little different, the Van Hoff factor. Okay, so we're going to do it with magnesium chloride. So let's say we have 0.32 grams magnesium chloride are added to a, I don't know, we'll say 325 milliliter solution of water at a temperature of, we'll do 27 degrees Celsius. Calculate the osmotic pressure in atmospheres. So first things first, we have to convert everything. So this is osmotic pressure, IMRT. So T has to be in kelvins, so let's do that first. So 27 plus 273 is 300. So you have 300 Kelvin. We have to figure out our molarity. So you have 0.32 grams of magnesium chloride. You have to convert that to moles. So I'm going to just do that real quick on my calculator to figure out the molar mass. So the molar mass is 95.211. So times 1 mole, 95.211 grams. So that cancels. And let's do that in the calculator. 0.32 divided by 95.211. And that's going to give us 0.0033 mole, I think. Let me double check that. 34. And that's magnesium chloride. Our volume has to be put into liters, so that's 325 milliliters times 1 liter divided by 1,000 milliliters. So that's 0.325 liters. So now we have to figure out the molarity. M equals 0.0034 divided by 0.325. So that's mole over liter. And that's 0.0034 divided by 0.325. And then our molarity is 0.0105 m. Alright, and then our Van Hoff factor. Technically you should do that first, but if this is dropped in the water and it dissociates, you're going to have magnesium plus 2 Cl negative 1. And this has to do with when I went over the periodic table like many units ago as to how many electrons elements are going to take or give up in their ionized forms. Has to do with the group numbers. So your Van Hoff factor is 1 plus 2 equals 3. So now we just plug everything into the formula. So it's 3 times, I'm going to write it on top, MRT. So 0.0105 m. So we're going to put moles over liter times 0.0821 liters times atmospheres, or moles times Kelvin, and then times 300 Kelvin. And then I'm definitely going to have to take this to the next page. So let me do that super quick. So let's finish this. You have moles cancels, liters cancels, kelvins cancels. So we're left with atmospheres. So let's plug this in the calculator. So you have 3 times 0.0105 times 0.0821 times 300. And that means our osmotic pressure for this instance is going to be about 0.78 atmospheres. And that's essentially how you would calculate if I gave you everything. You can also work backwards. I'm not going to do any problems because I've done many and you guys have practiced, so I'm not going to keep going over them. But say you needed to find the molarity or whatever. M is equal to pi over IRT. You need to find temperature. T equals pi over IMR. It's very, very interchangeable, so you just need to know what you're looking for, and these two you don't really have to ever solve for because this is a constant and I is the Van Hoff factor, so it's really just between these two. And that's pretty much it for this one. If you have any questions, please come by office hours.